All right. So, hi, everyone. Thanks for joining us in our MCLS February special. So, MCLS trainee board specifically. And we try to host these events twice per semester. So, this is our first one for 2026. So, thank you for joining us today. And we have four great panelists all over the world joining us and who will be discussing their research. And the format that we're going to be doing today is that we'll first have all of our panelists introduce themselves and a little bit about their research. And then we'll save the questions at the very end, which Nick will moderate. So you could either save your questions through the chat, or you could just keep it and then you could speak out during that last maybe 10, 15 minutes for the Q&A. Is that good for everyone? Okay, great. So to start off, we'll start with Dr. Dubé from McGill University. So fellow Canadian.
Hey, everybody. Okay, so I will just click share on this. Get this going. So let's see here. I want to share to this desktop. Okay, that's what I'll do. Okay, and then now I'll do, here's all seeing my lovely, my family's cabin out there. And then in a second, the slideshow should actually pop up. There we go. So people can see this, I assume now?
Yes, we can see it.
Fantastic. Okay. So start my 10-minute timer so I don't ramble. Hey, everybody, I'm Adam Dubé. I'm at McGill University up in Canada. I'm associate professor here, and I've been studying educational technology and math cognition since the start of my career. I'll be talking a little bit about my opinion on the relationship between AI and education first, because I give public talks on this, Children's and Screens, The Verge. And then I'll be telling you about my research, just one project that we've done in the lab to give you some insights about one of the things that we're doing and how we work with industry to apply AI and math cognition theory. And so first off, for everybody here that's jumped on this bandwagon since generative AI has come out, AI in education is not new. It's been around since the 1970s. It's been used for profiling and predicting which students are going to fail out. It's been used to assess students automatically. It's been used to design intelligent tutoring systems. And it's been used to develop adaptive and personalized systems. Importantly, for a lot of people here, most of this research has all been done by computer science researchers and STEM researchers, people who are in the mathematics department, not psychologists who study math cognition or education. So there's a gap here in who's actually doing AI in education, AI and math education research. So hopefully some of you will help fill this gap. Now, in terms of generative AI in education, there's thousands of these apps that already exist. They all say they do different things, but we've been doing systematic reviews on this, and basically they all serve three basic purposes. They're either a resource of information, which is you go to them like you would a book to get answers. They're a tutor that you interact with that's supposed to teach you how to understand something, or they're a tool that you use to get stuff done. And what we've done in our systematic review is looked at the research that's come out since ChatGPT has launched. And most of the research is on how people use generative AI as a tool for writing and higher education. There's actually very little research on generative AI in elementary education, very little on mathematics education, and surprisingly very little on how it's used as a tutor or as a resource of information. Most of it is people using generative AI to write. The other important thing is that what do we know about the evidence right now? The evidence is largely mixed. In our review, we just did a simple vote count, and we found that the largest number of studies had purely positive results. The next biggest was a bunch of mixed results. Now, one of the things I like to highlight here is that this is very common in early edtech research. A new technology launches, everyone gets excited, everyone runs a bunch of studies, they do short interventions, and these positive results tend to have very small sample sizes. This happens all the time. And then as more and more studies come out, we get a much better picture of what the actual impact of this stuff is. One of the first ones that came out last April or May was a meta-analysis in computers in education by Deng and colleagues. They said that, okay, we're seeing these big effects on learning outcomes and affect and motivation. But when you look at only short interventions, the effects tend to go away in these meta-analyses. When you look at longer durations, the effects tend to get smaller. And if you actually look at mental effort while people are using these tools, we actually see negative effects in those pieces. So students producing better outcomes in studies, like they're producing a better paper, but they're putting less effort in doing it. And that's questioning whether or not they're actually learning. And so I like to start with this, kind of gives you my framing. I take what's called a techno-skeptical approach to technology and education. I kind of look, how are we using it? How are we studying it? What's actually happening? And my assumption is usually that we're not getting it right off the bat. Now, here's an example of one project that we're doing in the lab on AI and mathematics games. These are some preliminary findings, just give you a hint of kind of what we're doing here up in Canada. This is a project lead by my PhD candidate, Jay Gao, and we've been working with Ulu Labs, a math company, a math game company here, been leading this industry for quite some time. They have a game called Math Makers, which is meant to help children understand fraction, multiplications, foundational concepts, even things like place value for kids from ages 5 to 10. Each level in this game is designed by math education experts, and they're very high quality. We've been studying their game and its impact, and we find consistent effects. The problem is that there's actually not enough levels for kids to reach mastery on the subjects they really have difficulty with. That's because it's hard for the designers to make enough levels by themselves and still be able to pay everybody. And so this is a difficult balance. High quality means low numbers of levels, which means less practice. So to solve this, they created a creative mode in this game. Now, in this creative mode, users will actually create levels themselves. So kids themselves, after a certain point, will start making their own math game levels. And the idea is that, well, you could have them make levels that other kids play so they could reach mastery. The problem is that most levels they make aren't very good. And you could say, well, let's use humans to identify the good levels, but then you have thousands and thousands of levels and you run into the economic problem. It's not financially viable. So how can we use this system to find good levels to help more kids reach mastery through game-based learning? Well, we're trying to use AI, specifically a machine learning approach. So we're using ML to create a classifier model that could look at these levels and say, these are levels that are most likely to be effective and of high quality. And then in the future, we'll create an adaptive system that will recommend those levels to kids. And so I'll tell you a little bit about this. So in this preliminary piece, this is basically what's happening. The kids are playing a pool of levels that designers have made themselves. Once they've completed enough of them, the advanced players then unlock the creative mode. I think you might be able to see my cursor on that screen. Once they unlock the creative mode, then a bunch of levels are generated that we have to filter through. Currently, it's human beings doing this filtering, and we're trying to figure out if we can use machine learning or AI to do this for us. And then try and basically replicate their expert evaluations that feed these levels back into the game pool so kids have more opportunities to have these good learning experiences. Now, to do this, what does it actually require? Well, we've got the data set right now of the existing levels, which are over 3,700 levels that are made by kids, and more of these are being generated every single day. But we're starting with this data with just 200 levels to try to get our hands around the problem. And these ones include both levels that are designed by the experts, which we know are good, and ones that are designed by users, which we've evaluated as either being good or not good. And those are expert evaluations from the game company themselves. And so one of the first steps we have to do with these things is that we have to take a game level and we have to turn it into a set of variables by generating this massive code book with hundreds of variables that we all have to semantically classify as being part of either the character or a goal in the level or the physics objects. So we go down and say, for example, here's a variable that equals the player character, the goal, a physical object, an obstacle. And that basically is trying to turn this into something that our machine learning classifier can actually read. So in this level, there's X number of platforms. There's a goal, which is the star. The star can only be reached once you clear the obstacle 20 by combining the game character here, 10, with this object down here near 10, which generates 20, which they can then use to break through the cloud. So theoretically, this would be an okay level that one would say, well, it's got all the pieces, you can complete it, it involves some sort of mathematics. Okay, now does the level that the player actually make, does it look like this? Or does it even look better than this? That's the challenge here. So we've created all these variables, identified all the pieces. Now, the problem is that there's a lot of variables that can be in these levels. Which ones actually matter? So in the first step, that we tried to reduce the number of variables we were looking at. So we had all the variables and put them into a lasso regression, which is basically like regression, but then you're basically doing a kind of like a cluster analysis to identify which of the variables within the model are most likely to predict a good or a bad level. So that way you can get a narrower set of variables that you can then use in your machine learning training. step. And so here, the lines to the left are ones that like, well, if this is present at a high amount, you're likely to reject the level, and lines that go to the bars that go to the right, if this is present to a high amount, you're more likely to say the level is good. So that's the first step that we had to do. The second step is that once we had these more limited number of variables that we could actually subject to these analyses, then we were testing 4 different machine learning methods. And each of these have a different underlying logic. And so if one is better than the other, then it kind of gives us some insights into the nature of the data sets. And so in terms of this, things that we do is we compare all 4 of the different types across different sort of outcome metrics. And we see, okay, which one of these does it succeed or fail at overall in terms of accuracy of predicting what is a good or a bad level. And the other thing that we can do here is we produce things like confusion matrices, where it tells us not just if it's a good or a bad level, but it's saying, okay, are the levels good at rejecting bad levels, but also at predicting good levels? Now, most of these models were great at rejecting bad levels, but only one of them was decently good at doing rejecting bad levels and predicting good levels. But it wasn't as good as predicting good levels as it was as rejecting bad levels. And so what we have right now in this process is we identified one machine learning approach, the random forest plot, as outperforming the others. This tells us that the patterns in our data aren't very simple. This means that the data likely contains a bunch of multiple overlapping patterns. This means that the features in the levels probably interact with each other. This means that there's a combination of features that matter more than any just say one variable or another that predicts what makes a good math level in a game. And this implies that a level isn't valid just because it has many goals or many characters. It's valid because of how all of these things come together. Now, that's a very abstract takeaway, but if you're connecting this back to math cognition, this matters because it tests how core elements of mathematical task structures can be translated into features that an AI system can detect and classify. It demonstrates that meaningful aspects of cognitive demand in math games are measurable computationally. We can say, yeah, we can actually create a system for saying, is this a good or a bad level that somewhat reflects what the expert evaluation is doing? It illustrates how AI can support adaptive learning. And it models, to some extent, a human-guided AI approach in which machine learning enhances rather than just replaces expert mathematical design, because we're basing the AI model on the levels that experts had selected. So we're trying to reproduce what they did, not instead just creating some criteria purely ground up, not driven by any human decisions. And so that's an example of what we're doing. And my watch went off, it's 10 minutes. You can check out our lab's website at McGill.ca/TLC. And on the left here is a new lab that we're building, 20 workstations, multimodal data collection for students interacting with PCs, with VR, with tablets. If you're interested in this type of stuff, check us out in the future if you go on to your master's or if you go on to a PhD or a postdoc. So that's it. And if you want, we're also putting out a book. If you have a chapter right now you want to get published, we got a book on math and AI that's currently, the call for proposals is closed, but feel free to still email us if you are a student here. Who knows? Okay, I'm done. I'm going to be quiet.
All right, thank you, Dr. Dubé, for that and how you showed us how we could use AI for adaptive learning in math. Now I'll give it to Dr. Anthony Botelho to go over his research.
Absolutely. And luckily, I think everything should now be sharing. So try and have a nice smooth transition there. Thanks everyone for having me. I'm going to be talking about a line of research that's really centered around one particular project that we're working on called Checkpoint, and I'll introduce that in just a moment. But just for the sake, I'll take the first 30 seconds at least to give a quick note of the type of work that I do in a more generalistic sense. I am one of those mentioned from the previous talk that started in the computer science side of things and started to kind of bridge my way across. But I'll argue at least I've started to make that bridge, that bridging a bit more than some of my other colleagues have. So I do work that's really at the center of computer science, statistics, cognitive psychology, education, many more ovals that I couldn't quite fit on one slide. But all at the intersection of all of these different fields of study, it's really important to kind of understand that each field is able to kind of provide new perspectives on how we are looking at math cognition, on education in a more generalistic sense, and thinking about how to bridge also gaps between the research that we're doing and how that translates into actual actionable practice. And I think that's at the core of really what I'm trying to do with my research in general. I do a lot of work with AI, cognitive, affective, and behavioral modeling. I do a lot of work with evaluation, looking at causal inference, trying to identify what works for whom and under what conditions, but ultimately trying to turn the research that we're doing into practical tools or applications or something that informs practice, trying to bridge, again, those gaps. And I would also, it is important for me to acknowledge the work of my students. I run a viable learning lab at the University of Florida. I'm an assistant professor in the College of Ed. So again, I bridged that gap, at least coming from computer science, now sitting in a College of Ed. And do a lot of amazing work with a lot of amazing people, at least one of whom is on the call. So thanks, Natalia, for joining in. But amazing work from all of my students, and all of the work that I'm doing here is many thanks to them and my other broader collaborators, many of whom I couldn't fit on one slide. So I at least had a nice balance of 5 individuals. But really, I think at the core of what I'm going to be talking about today, and I think a core question of my research in general, is this idea of how can we best design and leverage digital learning platforms, and I define that very broadly, to help teachers take action. Again, trying to make sure that the research that we're doing doesn't just end up in publication, but actually gets into hands of students and teachers that can make the most use of what we learn or otherwise what we build in what we're trying to produce. And really, the core project that this talk is centered around was stemming from a lot of participatory design work that we'd been doing with teachers, particularly in math cases, where we found that a lot of teachers rely on assessments to understand what their students know and what they don't know. Every action that they're taking, maybe not every action, but many actions that they take within a classroom setting is really based on their perception of what their students know, what they don't know, where there are gaps. So, and a lot of teachers utilize small, very formative assessments in order to assess that in a faster cycle. So after giving a brand new lesson on some new concept, typically it's the case that teachers might give something like an exit ticket assignment, something that's maybe 2 or 3 problems or 2 or 3 examples that have students practice the activity that they just learned about and use the information that they're gaining from that to then inform how they are setting up tomorrow's lesson, or worked examples that they're looking to give, or really just how they're kind of proceeding in their instruction from that point. But what we found from talking with a lot of teachers was that the formative assessments, these exit tickets, there are a lot that are already built into common curricula. So a lot of teachers were using illustrative math or Engage New York, some of these open curricula. And a lot of cases, there's a lack of transparency and often kind of a limited number of problems available to them. So teachers wanted to assess student knowledge. There's maybe 1 or 2 that's available for every unit or lesson within illustrative math. I'll beat up on that one for just a moment, although great curriculum, but again, there's limited numbers of items that they can give, and there's a lack of transparency in terms of coverage of every concept that a teacher is talking about or introducing is made up of many kind of sub-facets. There are different kind of sub-skills involved. Some of those might be calling upon prerequisite knowledge that they from previous lessons. Others might be kind of how to handle or think about whatever that concept is under different use cases. And there's kind of this lack of transparency in that they don't really know, just looking at the 2 or 3 problems in the textbook or in the curriculum, what the coverage looks like. So there's potentially overlap of many problems that kind of cover the same set of sub-skills while maybe even missing others. Sometimes this comes through if you've ever experienced the case where you do a couple of practice problems in math, think back to your middle school and high school days, and then you get the tests at the end of the week, and there are problems on the tests that look nothing like any of the practice problems that you did during that while learning the actual lesson itself. It's potentially recognizing that there's this gap of knowledge. There's some use case or edge case or sub-skill that was just not covered in any of the practice problems that you were given or anything that you've learned up to that point. Again, potentially kind of recognizing maybe a coverage issue. So how do we do this better? In this case, forgive my animation that I forgot about. It's also the case, like the same problem also extends to mathematics and education research, We also rely as researchers on good formative assessments. We use them for pre-tests and post-tests when we're looking at interventions. We try to look at how good measures of knowledge are helping us to relate back to interventions or instructional designs or whatever it is that we're looking to make impacts for. We use these assessments much in the same way. We're looking to kind of get more finer grained understandings of what students know and what they don't know. So again, what we tried to do was kind of cover both of those use cases by developing a tool which we call Checkpoint. It's misconception-focused assessments. If you also know me well, you know that I love acronyms, so I forced this acronym, the Comprehensive and Holistic Evaluation of Concept Knowledge and Progress for Optimized Instructional Needs Tracking, basically just to say that we wanted better ways of creating these assessments or helping teachers gain more transparency in these assessments. So really what this is at its core, it's an AI-powered tool. It does use LLMs for one part, but really what we wanted to do was try to detect from content, if we're given a set of content, some problems, how can we identify the optimal set of content that could assess student knowledge for a given lesson or a given concept. So really we think of it like an optimization problem. What is the fewest number of problems or the shortest assessment that we can give that covers the largest number of subfacets of some given standard or skill? And again, I'm throwing my hands around here trying to be as vague as possible, happy to boil down to specifics, but given some concept, how can we get the most coverage with the least amount of time that teachers actually need to devote to it in class? And we developed a little bit of a tool. If anyone wants to play around with it, you can go to the website. Right now, it's kind of in a functional prototype stage. If you do play around with it, we don't actually collect any data just yet. We're fighting with risk assessment at our university to make sure that we can actually be FERPA compliant. We claim that we are, but I'll save that argument for another day. But if you want to play around with the tool, you can use it to create some problems and assessments. Right now, what we're trying to do is identify from given curriculum, how can we select the items that have some amount of coverage and then use LLMs to generate problems that kind of fill in the gaps. So if there are certain recognized subfacets that are not covered within illustrative mathematics, how can we either find it from other curricula or otherwise generate those problems ourselves to be able to build those assessments in a more intelligent way? And again, from the name, we're also trying to think about different areas or what those subfacets actually mean. Right now, we're thinking about that from the perspective of defining misconceptions or conceptual or procedural errors that are typically made by students and trying to map those to subfacets. And as part of that, again, students can kind of do this, but we're really trying to understand more about kind of how this content actually reveals student knowledge and conception, and find out better ways of anticipating that and measuring that using different methodologies. And we're also taking AI approaches to that. So, for example, given some example problem, like simplify the following expression and explain your reasoning, we want to be able to understand, and again, we think of this as a prediction problem based on the features of this problem, the words used, the numbers that are found within, even just the structure, the kind of arrangement of things within the problem. How do all of those features map onto how difficult this problem is, both in terms of a perceived difficulty as well as a psychometric difficulty? How long would it take a student to solve this problem? Can we predict that in some natural way? We've done some preliminary work, and it seems that about 33% of the variance of both difficulty and time taken is attributable to this content level feature set. So ignoring the student, which student is actually interacting with this, just features about the problems themselves, the numbers, the structure, the words, that's explaining a large portion of the variance of these outcomes. So how can we use that to, again, construct better assessments and create this kind of learning nutrition label, thus the little nutrition label here on the side that we can stamp onto these problems, that also provides greater transparency for teachers. And again, try to understand then what we can say about what students know based on what they're how they're interacting with these problems. And very briefly, I'm going to skip over a couple of these. Very briefly, part of that is kind of exploring how do we separate conceptual misunderstandings from simpler errors that students might make. And there's a body of research that we're building on from that. And part of that would be utilizing open-ended responses and other behavioral and log data that we can collect from students as they're interacting with this to try to identify when students are actually have the conceptual gaps as opposed to when they just happen to forget the negative sign when they put in their answer or made a careless slip along the way. And part of this is also extending from building much more than just what students give as their answers, but also thinking about how they engage with the problem itself as a measure of what they know and how much they know, how much effort they're putting in, how much time they're devoting to kind of planning versus actually answering the problems themselves. The timing information is actually also really important to understanding which errors might be attributed to conceptual gaps as opposed to kind of procedural errors that students are making. And all of this could be used to kind of create a more holistic view of what students know to inform how a teacher might be able to kind of progress from this. And was also kind of mentioned earlier as well, beyond even just time and other things, there are decades of research of AI in education that have produced a lot of different detectors of cognitive, affective, and behavioral measures. So what we're also thinking about is how these can also be used to create this kind of triangulation of what students know and try to understand the relationship between all of these factors. So that way, when students are engaging with this content, we have a better understanding of, again, not only what they know, but also motivational factors, different ways of maybe approaching their remediation or further instruction, so that we also know the right way to approach these students. And this is a very hard challenge, so don't think that I have this solved by any means, but these are some of the open questions that we're currently grappling with. But for sake of time, I'm running close here, so let me stop there for a moment. I gave you a very high level, at least, of some of the things that we care about and what we've been thinking about. And thanks again to the students who have been helping to make this happen, but happy to then give up the mic. So thank you all.
Thank you, Dr. Botelho, for your presentation on your research assessments and, the assessments that reveal students' conceptual and misconceptions. I'll now pass it on to Dr. Elida Laski from Boston College.
Great, thanks. Let me get this out of the way. Right, so I'm coming at this from a different perspective. So somebody with not much background at all or any in computer science, really somebody who's interested in early math development and establishing sort of the trajectories of math learning and how we can support math learning. And recently I've been pulled in the direction of looking at the home math learning environment as a place of supporting math learning. And in collaboration with some colleagues, we're developing an app to try to support parent-child math interactions at the home. And this app is called PAL, which is an acronym for Personal Assistant for Learning. And you can see the website here, the https pal.guide, if you want to take a look at it. But I must acknowledge that this work is done in collaboration with two amazing people who work at Learnology, actually created this Learnology Foundation, Dr. Anastasia Betts and Benjamin Ryan, and this work would not be possible without them. They're really sort of the lead on the project, and I've just had the benefit of working alongside them. So in thinking about the home math environment, there's been an increased recognition of parents' role in supporting children's early math at home. And I think there's been a proliferation recently of apps trying to support parents in this. And the approach that a lot of apps have taken is sending text-based nudges to parents. So reminding them, telling them about the importance of math, or saying, hey, here's a math activity you can do with your child, and sending these text-based nudges on some sort of consistent basis, maybe once a week or so. And when I was talking to Anastasia, we identified what we thought were some sort of issues with those current approaches. One is that it seemed to treat all children sort of as monoliths, where you're sending the same activity out to every family at every time without any consideration of differences and individual differences in children's skills or parents' sort of ability to facilitate these. They tend to look at the adult side as sort of just focusing on helping adults understand that early math is important without providing them any sort of information about the process of math. So we wanted to think about how we could simultaneously, in sending out these activities and nudges, help parents understand sort of the trajectory of different math skills and how they can scaffold math in different ways. We also thought that a lot of these apps were sort of largely unresponsive to the ecological sort of realities of families. So you can keep sending out nudges all the time, but they can get this sort of notification fatigue where they see it, they might click on it, but they don't necessarily act on it. And there's no way of really keeping track whether they act on it or knowing the right number and time to send these notifications. And then finally, we thought that while it's really important to sort of focus on the home math environment, a lot of these apps then sort of start isolating the home math environment from other learning contexts and don't find ways of bridging them. So in trying to address these shortfalls, we designed PAL to sort of rely on AI behind the scenes to address some of these shortfalls. So the PAL Assistant for Learning is a human-mediated smart system. So the children themselves do not engage with the app. Rather, it sends nudges to the parents so the parents can still engage in that one-on-one, in-person kind of instruction and early math support. So as with other apps, it sends these short, developmentally appropriate math activities via text. And these activities are absent of screens. So it comes via the ed tech, but it doesn't involve ed tech to do these activities. So they're really designed to amplify the human teaching, not to necessarily automatize it in this situation. What we've been using AI behind the scenes to do, so with models, is to use the data to identify what each child is most ready to learn, so that we are not just sending out texts that are sort of treating children as monoliths, but that the activities sent to parents are sort of tailored for the particular child's learning needs. And we've been exploring how to use AI to guide when adults might be most ready to interact. So we've been using sort of parents' engagement with the app itself to indicate when are sort of the elevated times that nudges might be most beneficial. When have they closed the loop and actually engaged in the activity? And rather than sending out a massive number of text nudges sort of at any time, we're sending out fewer text nudges at particular times based on user interactions. And then there's also connecting this to a teacher dashboard where the information is shared with teachers. So we're trying to find ways to share this resource and the information that it's generating across both home and school. So how PAL works is that parents receive a text message with a link, and then they click on the link to choose the activity. They do their activity with the child, and then they're supposed to tell PAL, and this is the novel piece, I think, how their child did with the activity. And initially, we gave parents one of three options. So they did it really easily, they did it with some help, or they really struggled. And you can see how this sort of relates to the Goldilocks principle or CPD. What we found was what we found and what we suspected from piloting was that parents were pretty bad at judging how to respond to this. So if the child made any mistake, they thought the child was really struggling and failing, rather than sort of understanding that some mistakes are actually mean they're on the cusp of learning. So under the hood, what we've built is a really detailed knowledge model that was based on sort of the existing research, a really thorough literature review, tapping in different expertise, so that we have told the system under the hood what skills are related to early math, how they're related to each other and what the developmental progression is. So this knowledge model drives the feedback that we get from parents about how children are doing, and then determines what activity they're sent next. So it predicts based on the parent feedback what the subsequent activity would be, or whether they need more practice in that skill before they achieve any sort of mastery. And then it dynamically adjusts, much in the ways kind of a cognitive tutor would, right? But that is dependent, as I said, on getting the parents' feedback about how the child did with the activity. So rather than just having parents select from one of 3 potential options, we've now sort of moved on to another version where we use LLMs to have the parents describe the child's behavior during the activity. And then we have sort of programmed in what we know are typical misconceptions, typical errors. And so now we can give even more refined feedback, and the system can use that to map it onto the knowledge model to determine what activity to send out next. The other thing we've been, so this was our initial approach, and we've moved on from that. So we've done a pilot study of PAL compared to just a business as usual. So we randomly assigned one classroom of children to use PAL and for their parents to engage with PAL, and another classroom was just the business as usual. And we found significant gains in learning gains pre-post amongst the children who use PAL relative to those who were in the business as usual group. And importantly, there was also a correlation between how much parents engaged with PAL and the pre-post test gains. So we knew that this engagement piece really mattered. And so that's where we started exploring how we could do temporal scaffolding. So the system pays attention to when there is this closed engagement loop. And the closed engagement loop would be the parent not only clicks on the activity, but also reports how the child did in the activity. And so then we know they've closed the engagement. And based on the time of days and the days of the week in which we actually see these closed engagement in the first few days of interaction, we begin to send the nudges only during those times. And what we found is that temporal scaffolding leads to greater closed engagement loops. So overall, you have fewer nudges, but you have still greater engagement. And so we have sort of this trade-off that exists, but we think that it's making the system even more effective. The last piece is how this relates and connects to the classroom. So teachers themselves can actually have dashboards that show the entire knowledge model. And they can see, based on the parents' feedback, where individual children in their class are seated in the knowledge model. So a node is a particular skill, and that node would be green if most parents are reporting that children are doing the activities related to that skill quite easily. It would be yellow if they're sort of still in the learning process, or red if a lot of parents are reporting that they are still struggling. Then teachers can see sort of individual children's knowledge models, as well as sort of averages across their class. Teachers can go in and they can suggest particular activities themselves. They can override the system and suggest particular activities related to skills that they might be practicing at school. They can also provide feedback to the system based on their observations in the classroom, so it can merge the data to create a stronger knowledge model for each child. And we are looking to explore ways in which how teachers engaging with these knowledge models might actually support teachers' own understandings of math trajectories and math projection themselves. So the dashboard allows them to see sort of these grade level milestones or also to sort of have a visual map of how concepts and skills interact, and how quickly, when you achieve one skill, you start seeing other skills being achieved as well in terms of the parents' feedback. So that was short and sweet.
Great. Thank you for that and showing us your research on how we can use apps that support parent-child math interaction. I'm a bit biased because that's my research, so I thought that was that was really good. But in terms of time, I'll just pass it off now to Dr. Marrone, joining us all the way from Australia to present her research.
Thank you. Let me just share this. Perfect. Okay. Well, yes. Thank you, Fräulein, for that. So, yeah. So today I'm just going to be talking a little bit about some of the research that we've been doing around how can we help students feel better about learning maths. So, just a shout out to some of my colleagues here. So, Dr. Florence Gabriel, who's also in this call, and Dr. John Kennedy. Lots of the research that I'll be talking about, we've done together. At Adelaide University. So both Flo and I have more educational psychology backgrounds. And so lots of our perspective and interpretation comes from that. I just want to start here with, I guess, the problem as we know it, the issues with math anxiety. Sorry, I will say that in Australia we say maths. And so I apologize. I've realized that everywhere it says maths, but please, I am talking about math. But some of the research that we've been doing shows that students are feeling these negative attitudes towards mathematics as early or as young as 5 to 6 years old. So a few years ago, we worked with a school here in Australia. We followed students for over a year and just looked at how their attitudes developed. And yeah, we unfortunately saw negative attitudes and some really strong kind of negative words towards mathematics in students that were really, really young. And so this kind of led us to a theoretical approach to kind of understand why is this happening. And this paper has just come out in Science Learning. So you can see it just down the bottom, but it's just a framework, so a control value theory of achievement for emotion. So basically, we know that maths anxiety emerges when students value a subject, but they perceive a lack of control over their performance. And there's the reinforcing loop there. So the virtuous cycle where success is social emotional learning growth, so you have greater control, more success, or the vicious cycle, the loss of control, increased anxiety, and then therefore a further loss of control. And so our paper talks about how we believe that AI can intervene in both loops there. We've proposed kind of 6 roles here for AI in the learning process. So taking that control value theory approach. So AI can personalize the task difficulty and agency, which is what we've seen the fellow speakers talk about today, so looking around individualized achievement, goal structures and expectations, improved value induction, moderate feedback loops, retraining or reframing success, failures and beliefs, and fostering self-regulated learning of emotion. So again, lots of the work that we do comes from that self-regulated learning perspective and how can we give agency to students. But that framework and that kind of early research where we saw those really negative attitudes in really young students kind of led us to a question of, can a cognitive behavioral therapy based chatbot reduce maths anxiety during testing? So a few years ago, actually, with Professor Erin Maloney from the University of Ottawa, Fräulein, and colleagues, we were sitting around discussing, okay, well, we know we have these problems, but what can we do to kind of reduce those feelings of anxiety, in particular during test taking situations? And one of the reasons is because I was one of those students. So I was an early high school student who could do mathematics when it, was in class, but really struggled and had a lot of maths anxiety when it came to the test. And so we thought about, can we do a randomized control trial that compared chatbot delivered CBT strategies against either positive feedback, printed strategies, or a controlled condition. We thought this was going to be super easy, and we thought, okay, we'll trial this with undergraduate students, and in no time we will be doing this with elementary students or really young students here in Australia. But what we found was not the case. And interestingly, so we created this working example of the emotionally aware AI support. So we just called it Chatty. It's a proof of concept AI math anxiety support bot. demonstrates how AI can go beyond simply providing answers. So this was created in-house by the team that I work with at the Centre for Change and Complexity in Learning. So most of the team that we work with is data scientists, and then Flo and I do a lot of the educational psychology things alongside it. But basically, the chatbot is designed to support students to help them manage their emotions during a test, provide encouragement, and then it runs in that closed kind of safe environment. And so the question we have is, yeah, what if AI doesn't tutor maths, but directly targets the anxiety itself? The study design was just 4 conditions, randomized design. So we had a CBT chatbot, a neutral chatbot, a printout, and a control. The CBT strategies were really kind of simple and basic. So would take the students through something like deep breathing, cognitive reframing, mental imagery, confidence building, physical breaks, or positive recall. This was just kind of the study flow, if you like. So we pre-test looked at students' test anxiety and state trait anxiety. We gave them an introduction to the tool. It was a maths test that they had to do that obviously increasingly got more challenging. The post-test and the debrief. What's the most interesting is after 2 rounds of piloting, we found kind of contradictory results and also some quite concerning things. So the first pilot, nobody used the chatbot, which we thought was quite interesting. And the feedback that we got is students were so anxious. So we inadvertently increased anxiety in these students. And I will say, so these are undergraduate students who, it was a fake maths test. They got credits and paid to take this fake maths test, and we made them more anxious, which is problematic for a number of reasons. But the solution for that was we added 5 minutes of extra time. We strongly encouraged students to use the tool, and we gave them some pre-test tutorials on how to use it. The next challenge we found was that the strategies were skimmed, so not thoroughly read. So it would take student through a cognitive reframing or a deep breathing, and the student would read it and just click, it didn't help, and move on. So they weren't actually taking the time to engage in the practice. Students found that the usefulness was too vague. So we were replacing the terminology with specific items, and we went a little bit more direct, a little bit harder on some of the CBT-based strategies, if you like, as opposed to saying, this might help you. We were saying, it will help you minimize your negative feelings. It will help you perform better, just to try to see if we could shift student use. And the AI familiarity items were double-barreled. So we changed the subscales that we had. The piloting was essential. So what we learned here was that our initial assumptions about engagement were fundamentally wrong. So where we thought students would automatically engage, automatically find value, and automatically continue using, they did not. And so we now have the full data set from that, and looking at analysing that to then see how can we take this out of a higher education setting and into elementary and secondary school. So the questions that we were kind of left with here around the what's next, or where are we going with this research, was, does CBT actually work compared to encouragement alone or the printed strategies? Do students actually choose to use the chatbot? Why or why not? Which CBT strategies do students find the most effective? Does the AI delivery mechanism matter? And how does AI literacy shape engagement? And I think I'm really grappling at the moment with what is the value of AI in this. And when we're looking at, in particular, reducing, anxiety with students during these test-taking situations, are we seeing any added value above and beyond just regular CBT? Or regular, encouragement of students in these test-taking situations. And so at the moment, it's a real conversation around why should we be using AI, not is and how it's working, but what is the value add for these tools in our space. And so please, if anybody is interested, we would love to obviously continue doing this research and working together to explore and unpack some of this in classrooms. So I will end it there. That was just the DOI for the paper that I shared. We have just merged universities here in Australia or here in South Australia. So if you look us up, I just suggest you just Google C3L Adelaide University. The website is not fantastic at the moment, but please otherwise just reach out, and I'm more than happy to chat and connect. So thank you.
Thank you, Dr. Marrone. Great. I'm really impressed with the versatility of the tools described today and their implication for math cognition and math learning. I really appreciate all the speakers that joined us today. So we don't have a ton of time for Q&A. I think that's a representation of the volume of the research that's happening right now in AI and math learning. So that's totally okay. And maybe I'll volunteer the speakers a bit here and say, I'm sure you could reach out to them if you have specific questions for them. I'm just going to go in order in the chat until we run out of time. And so this first question is for Anthony specifically. And the question is Checkpoint reliant on open educational resources, or did it train on other materials as well?
So I can, very quickly, to add more time for questions. It's not reliant on open educational resources. We did start there in terms of just support and what we were looking at, just to have the largest potential effect. A lot of teachers are already using those materials. They're widely used. I think illustrative specifically is like the #1 curriculum used across the US. So we wanted to start there as a way of kind of making it easier for teachers to onboard to either using our tool or otherwise the things that we learn by looking at that data would also be more broadly applicable. So we're already starting to look at publishing just open resources that are just measuring the psychometric properties of illustrative data and just putting that out for others to benefit, while also, again, incorporating it into our platform. And just as a final note, a lot of what we are doing in terms of like training the AI and other things, that does come from other digital learning platforms, whether through open source data sets. So there are a ton available on places like DataShop. There have been large initiatives for creating open data sets and open things for others to use. But we also do have partnerships with platforms like Carnegie Learning, Assessments. That some of these other platforms are really dedicated to supporting research. So we've also partnered with them through other initiatives like SeerNet and some others that you can also learn more about. Happy to share out all of those resources for those interested in learning more.
Thank you. And if anyone does have resources they'd like to share, I'm sure you can just throw those in the chat. I'm going to move on to Natalia's question, and this is for Elida. So how do you go about cybersecurity, especially since it sounds like the Gen AI that you're using may have access to young students' informative and family-related data?
Yes, I don't know the details to that, but I do know that it's behind a secure server, and I would have to ask Ben that information. It was good enough that it got IRB approval. That's all I can say.
Yeah. Well, there we go. Natalia can follow up with you. So thanks for the question. Okay, and then we have another one for Elida. So can you send videos through the platform, or is it just SMS, maybe other kinds of multimodal
Yeah,
data as well?
Right now, the text messages can send links to videos, and we've actually had videos training parents, if you will, on sort of the importance of math, on ways to identify their child's level at different math, about the progression between different math skills. But at the moment, all the activity descriptions are text-based.
Just catching up on the questions here. I saw you responded to a few, so thanks for doing that.
I thought I would save time that way, but yeah.
Yeah. Okay, let's see. So does PAL survey does it collect data from parents to learn more about home engagement activities that may vary due to cultural?
Yeah, so in the initial iteration, we did parent surveys just on, separately as pre-post testing. We also did the TEMA separately in person. But we've now been working on actually embedding these things into the app itself. So parents will respond to some questions about their characteristics, their math self-efficacy, their time for teaching math, their math anxiety, math beliefs, these kinds of questions we've all used in our home environment scales. And we're also have created, and we're close to sort of, I think, validating it, what's essentially a digital tema. And so we're trying to automatize the pre-post testing, but also have a different version that's adaptive, which will provide the system more information to level the children on the knowledge model.
And then, you know, this is almost like a good question for the whole team here, but so what can folks say more about the relationship between parents and teachers? So maybe Alida, in your context, are you working with teachers with your application?
Yeah, so the way we're recruiting parents primarily is through teachers. And so we invite the teachers to use the app and invite their families to join, much the way like a class dojo or parent square, these kind of parent communication apps would work. So they actually onboard the children themselves by sending out an invitation. The parents accept the invitation. And so their dashboard is built when parents accept the invitation. And then they can see the connection between the feedback the system is getting and it appears on their teacher dashboard.
Thanks, Alida. I think that your series of questions for now. So Rebecca, it looks like there's a question for you. Have you guys considered adding a before question space where students have to do some of the anxiety diminishing activities? Like they could have 3 minutes and then have access to the next math or question, but that wouldn't necessarily require Gen AI coming from a student that felt a lot of math anxiety.
Yeah, so we definitely have considered, do we just force them to, undertake these CBT strategies? But obviously that's, can be consequential for your study design. I think more than anything, it's probably raised questions around, like I said, the value of AI and the use of AI in these kind of settings, and how should we be using it to best support student learning. And that needs to be kind of driven by the student. So having it available because it's cheap, it's easy, you can do it at scale, something that we can have alongside there, but it doesn't necessarily have to have a value add for everybody. And that's still up to, the learner to engage with those tools or with those systems, how they see fit. But we have definitely considered just forcing everybody to use it and see what happens there.
Thank you. Any other questions? We've got a couple minutes here. Free to speak up if you'd like to, or put it in the chat.
While we're waiting for other people to have questions, maybe are typing it, I do want to highlight that Anthony sent a bunch of resources that people were interested in using AI research in the comment section. Many of these he's highlighted are US based. So just yeah.
But if nothing else, what I'll maybe point out there why I was sharing those, it seems like at least there's this growing effort to connect education researchers with the data that's being produced by a lot of these technologies. Again, those first two links that I put there are specifically philanthropic funding being drawn around this, as well as federal funding that are specifically looking to produce large data sets that could be openly available and produced for supporting just open educational resources and again, just improving the greater good. So to nothing else, if nothing else, I think it's showing that there's a lot of interest and kind of growing, growing power in that direction.
Infrastructure.
Yeah, I will I will add that. So on that, I guess the international kind of lens in Australia, we are super keen to do this research and to do AI research at scale. So for people, like I said, who want to collaborate or who want to collect data in other countries, we absolutely have the ability to do that here. And yeah, our education systems are keen and supportive. So if there's any cross-country collaboration that people are interested in, then yeah, more than happy to do it here.
Thanks for that. All right, well, we are at I just want to thank the presenters again, and thanks everyone for joining us today. This was a really interesting and great session, and this will go up on YouTube, I should say. So if you missed anything or you want to find some of the links that were shared today, you can go onto our YouTube channel, MCLS Trainee, and you can find information there.